Today we are going to record a short video lecture on linear algebra, a subject from the branch of mathematics, and this is a course in our university in second semester MSc Mathematics program. So today I am going to introduce something called vector spaces, and which has wide applications. As we know, mathematics has application in the branch of engineering, physics, and many other branches. So like for example, in engineering, we have signal processing. So signals, input output signals can be, they are like functions in mathematics, and like we can treat, we can add, we can multiply functions, in systems engineering, the foundation is vector spaces, where the vectors are actually functions in system engineering. So it has wide applications, as I said. So let us introduce vector spaces and few properties and few results we will discuss today. So vector spaces, we define vector space like is a non-empty set of vectors. Non-empty, a vector space is a non-empty set of objects called vectors, and we define on these objects two operations called define two operations on these objects called vector addition and scalar multiplication. And if V satisfies the following 10 axioms, axioms are nothing but rules, then we call V a vector space. So as I mentioned, let me state those 10 axioms that a vector space has to satisfy. And these axioms are true for all vectors u, v, w in V, u, v, w in V for all vectors, and all scalars C, D. So number one, this when we add two operations, we said addition and multiplication, scalar multiplication. So when we add two vectors, this must belong to the set, the vector space, the set V. Number two, that means this is called closure. This is called closure property. And if we add three objects like this, three vectors, then it is called associativity. We can associate any two, means we can add uv first then w, or we can add vw and then u. It's all the same. So this is called associativity. then u plus v is same as v plus u. This is called commutative property. So the addition must satisfy commutative property also. And then for any u, there must exist an element denoted by 0, so that there is no effect on u, it remains u. So this is additive identity. It's called 0 is additive identity. And the fifth one, there are 5 properties in respect of this addition operation. So the fifth one is for each u in the set V, there is another element denoted by minus u, such that u plus, when I add these two, I get the same additive identity which is mentioned here in rule 4. So these 5 rules, then we have the total 10, and then now the other rules, other 5 will be in respect of the scalar multiplication. So if I multiply any vector by a scalar c, then this must belong to the vector space. So it is closure property of scalar multiplication. So when I multiply, it belongs to V again. And then if I multiply like this, sum of 2 vectors by C, then this distributes over these 2, so it becomes Cu plus Cv, this distributive property. And then if it is C plus D, 2 scalars are added like this and multiplied by a vector u, so this also distribute over these 2, so it becomes Cu plus Du. Okay. And number 9, if we multiply CD, 2 scalars, and then a vector is multiplied with this, then this is same as C du. And finally, number 10 is the multiplicative identity. This identity exists such that if I multiply with any vector, it remains same. There is no effect on u, it remains same. So any non-empty set V, if it satisfies under these 2 operations, these 10 axioms or rules, then we say that non-empty set a vector space defined over the field of scalars. That field of scalar may be real number or any other field of scalars. So we say it is a vector space. So let me move to, we have very short time, so let me move to another important term called subspace. So we'll see what is a subspace. So of course it is a subspace of a vector space. We must have a vector space first, then we can define a subspace. So suppose visually if we want to see, suppose this is a set and this is V, the vector space, then we are talking about a subset of this, let me call it H. So H is a subset of V. Then any subset will be called a subspace if this itself is a vector space by itself under the same induced operations from the vector space V. Same operations, vector addition and scalar multiplication. So what I mean, if this is a subset, number 1, it is a subset, number 1. Number 2, it satisfies all the 10 axioms that I defined for a vector space by itself. Under the same operations. Okay. Then we say this subset a subspace of V. So, so that means it is a vector space by itself under the same operation. So, while verifying whether a subset is a subspace or not, we need not go back to those 10 axioms, but we can simplify, we can reduce it to only few rules to be verified, few properties to be verified. So, what are these? A subset will be a subspace of V if only these are satisfied. Number one, it should be non-empty. Okay, non-empty means at least one, namely this 0 must belong to H. 0 of V must belong to the subset also. The 0 that was here must belong to H also. And number two, if I add any two vectors U and V in H, for any two vector U and V in H, if I add them, it must belong to H. This is the closure property again. And number three, scalar multiplication. If I multiply any vector by a scalar, then this also must belong to H. So, instead of verifying all the 10, we can verify only these 3. And further, one can combine this number 2, number 3 and make it one condition by writing like this. If it is if we can say for UV in H and CD and scalar CD, if this is satisfied, CU plus DV, suppose if we can show it belongs to this. So, instead of these two conditions can be reduced to a single condition, this one. So, we can verify whether 0 belongs to H and whether for any two elements U and V in H and two scalars C and D, whether this belongs to H or not. If it belongs to H, then we say it is a subspace. So, let us now move to the union, intersection, and we'll discuss this few topics, few terms like union, intersection, sum, and direct sum of subspaces. So now we know what are subspaces. So given a vector space, we may have subspaces, and then what is the intersection, union, sum, and direct sum of subspaces, that we'll discuss. So for example, we have a vector space V, and suppose there are two subspaces, okay, two subspaces, let's say I call it U and I call this W, okay. So this part that you see, the common part of U and W is called intersection. So this is nothing but U, we denote it like this, U intersection W, so which is nothing but common of U and V. So any element here, if I take any element here, it belongs to U as well as it belongs to W, and moreover everything is inside V, okay. So any element here will be inside V. So U, if it is here, it is in U, it is in W, it is also in V. So it is easy to verify whether this intersection, this part, is a subspace or not. Of course, this is a subset of V, it is a part of V, that's how it is obviously a subset, but whether it is a subspace or not, it has to satisfy those three conditions as I mentioned. So 0, for example, it's very easy to verify that 0 belongs to U intersection W. Why? Intersection means which is in both. So we know that what we assumed, U and W, these are subspaces. So since these are subspaces, they contain 0 of V. So this also contains 0 of V. So we know 0 belongs to U and 0 belongs to W. So anything which is common in U and V is that belongs to the intersection. So obviously this 0 belongs to U and V. And then if I take any two element here, okay, I can show that like if I take U and V belongs to the intersection U intersection W, then I can show that their sum also belongs to U intersection W. It's very easy because U and V in intersection means it is in both. So U is a subspace, so by property of subspaces this belongs to this, this belongs to both, and hence it belongs to the intersection. And similarly, this also we can show for any U in the intersection, this also belongs to the intersection. So I am not going to the detail, but it is very easy to show. So this, what we can conclude, the intersection, or we can generalize also. This is two subspaces I am taking. It could be any number of subspaces. So intersection of any number of subspaces will be a subspace of V. So this intersection is a subspace. Then what about union? Union means it is this whole thing, So an element that belongs to the union, it is denoted this U union W, it is denoted like this, it is the union. But union means it is anything which belongs to U or W. So it is the whole thing, this whole part, and that obviously includes the intersection as well. So obviously the union is a subset of this V vector space. So subset, it is a part of this, so it is obviously a subset, but whether it is a subspace or not. So for that we have to verify again those three. Number one, whether the 0 of V belong to this or not. Now since U is a subspace, W is a subspace, so 0 belongs to both, and hence obviously it will be in the union. So first 0 belongs to union is okay. Let me verify number 3 first before 2. So number 3 says scalar multiplication of any element. If I take any element anywhere, let's say U here, then if I multiply by a scalar, whether that belongs to, so if it is here, it is in union, and we know it is in the subspace U. So since this is already subspace, so scalar multiplication belong to U. So if it is U, again it will be in U in union, so W. So this is satisfied, U union W. So this will be in union. But union is not a subspace because this number 2 fails. Number 2 criteria fails. Why? Because if I take two elements here, U and V, then it is fine, it is in the intersection, and hence it will be in the union. Again this U plus V will be in the union. But imagine if I take U here and if I take V here, then there will be no property which will guarantee that U plus V that will belong to the union. Okay. So this number 2 property fails. Okay. So whenever a theorem fails, it is in mathematics, it is proved by a counter example. So you can we can think of a counter example. Let's say the vector space V, we take it as R square, which is nothing but this Euclidean plane that we have x axis, we have y axis, and we are talking about this whole plane, xy plane. So that is what is R square. So in this is our vector space, okay, and if we take U for example, a subset of V or this plane denoted like this, like A0. These are now vectors A0 or points on the plane. So A0 such that A is a real number. Okay. So what is this? This is nothing but, this is the plane, this is plane, the whole two-dimensional plane. And what is this? Is nothing but it is all the vectors of the form where first component is some real number and second is always 0. So we know these are nothing but points on the x-axis. So this is nothing but x-axis. And W, if I define like this, 0 B such that B belongs to a set of real numbers. So this you can see it will be points of the form where the first component or the first coordinate is 0, second is B. So these are nothing but 0 means it is on y-axis. X is 0, y is B. So it is always in y-axis. So this is nothing but it is representing y-axis. Okay. Now imagine what is the union. Union of these two sets. Union of, and we can see these are nothing but subsets of the plane, part of the plane, and they themselves are subspaces. It can be easily verified. Okay. So we are talking about or interested to know what is U union W in this case, in this particular example. So it is nothing but, you throw in all the elements of x and throw in all the elements of y. So it is only this axis, not the whole plane. It is not this. It is only the axis, these axes. Okay. So the points lying on this, the vectors, they lie on this point, on these two lines. Okay. So we can see if I take any value here, let's say this is 0, 2, okay, the vector 0, 2, and the vector 3, 0, for example, and if I add them, I take one element from here, I take one element from here. So what I am doing is that property 2 fails as we verified earlier. So 2 says that the sum of these two, 0, 2 plus 3, 0, see, note that these two belong to U union W, U union W. They both belong to the union. Union means combined, these two axes combined. So since these points are lying on the axis, so they belong to obviously the same union. But when we add them, we get component wise, we add 0 with 3, so we get 3. We add 2 with 0, we get 2. So what we get is, if we locate this vector on the plane, it will be 3 and 2, that means this one. So 3, 2 vector is represented by this point, which is not lying on these two axes. That means this does not belong to U union W. Okay. So this second property is violated. So this is an example or a counter example. This is what? Counter example, you can say. A counter example to show that the union of two subspaces need not be a subspace. The union of two subspaces need not be a subspace. And the proof is here. This counter example shows that it may not be a subspace. Okay. So this is about union. So union need not be a subspace, but intersection of any number of subspaces is a subspace. Okay. So this we have seen, and now let us see what is the sum. What we mean by sum? Sum of two subspaces. So how we define the sum? We write U plus W, okay, where U and W are subspaces, and we denote the sum like this. And how we define it? Contains, you know, elements of the form 1 U plus small w, okay, such that U belongs to U and W belongs to W. That means the sum is defined like it's the elements which can be written as, you know, one element from this, another from W, and all such elements, they form this set called the sum. Okay. So, for example, what is the sum of in earlier example we have seen? If I take the same example where the vectors are A0 and W is 0B, okay, and our V is of course the plane R square, R2. So, what is the sum of these two? That means I have to take one element from here, I have to take one element from here, I have to add them, and then I get an element here in the sum. So, what type of elements we will get if we see? So, U plus W will be like adding such elements. Here elements are of this form where the first component is any real number and second component is 0, and here first component is 0, second component is any real number. So, when we add such elements, we get, you know, elements of the form A, B. A plus 0 will be A, 0 plus B will be B. So, we will get like this where both A and B, they are real numbers. Now, see what is this? It is vectors of this form, and where A and B are any numbers, any real number. And so, this is nothing but what? This is nothing but the whole space R square. This is what is our V. Okay. So, this is an example of subspace. So, what is done here? If we want to visualize, this is the set U. This axis represents U, and this axis represents W. And what is U plus W? When I add them, I get the whole thing, whole plane, because I will get elements of this type where that represents any point on the plane. But unlike this one, what was U union W? It's not like this. It is only this two, this axis. I mean this axis, this axis. So it is collection of the points lying on this line as well as this line, not this part, not this part. Okay. So this is the difference between the union and the sum as it is defined. Okay. So then there is a theorem I would like to state in this regard. So the theorem says, that if U and W be two subspaces of V, a vector space, then so is U plus W. That means if U and W are subspaces, then U plus W is also a subspace. So it's again very easy to prove. So here we'll see this theorem says that U and V, if they are subspaces, then U plus W is also a subspace. So for any set to verify it is a subspace, we mentioned that there are three conditions must be satisfied. Number one, 0 of the vector space must belong to U plus W. So this we can verify easily. 0 belongs to U. Why? Is because U is a subspace, and any subspace must contain 0 of the vector space. So it belongs to this. Similarly, 0 also belongs to W, the same 0, the 0 vector of the vector space V also belongs to W, and hence whenever this, we can combine them, we can write 0 plus 0, and this is nothing but 0 only, this 0 of U and this 0 of V, and since both of them is 0, and you know, whenever elements are of this form, 0, this from U, 0 from W, of course they are same 0. So this type of pair of elements, they belong to U plus W. So it's very easy to verify that if U and W are subspaces, then if U and W they contain 0, of course U plus V, the first condition, 0 belongs to U plus W. So the second one, that two elements if we take from U plus W. So two elements like U1 plus W1, one element U2 plus W2, because elements of U plus W, they look like this. One component will be from U, one component from W. So I am assuming these two belong to U plus W. Now we have to see their sum, whether the sum belongs to U plus W or not, because this is the second condition. Sum of two vectors must belong to the subset to become subspace. So if I add this like this, okay, then can I write this as U1 plus U2 plus W1 plus W2. Can I write like this? I can, because you know those 10 axioms at the beginning that I mentioned, one of that was associativity of addition. That means when you add 3 or 4 or more vectors, you can associate any two first. So here U1 and W1 were associated. Now I am associating U and W. This can be done because of that property of associativity. So if this, we can write this two like this, and hence you can see these two U1 and U2, they belong to U. Both U1 and U2, they belong to U, and hence their sum, because it is a subspace, so this belongs to U. Similarly, this, both of them belong to W, and W is a subspace, and hence their sum will belong to W. So you can see we have some value here which belongs to U, the another which belongs to W. It's a combination like this, and that's why this sum of these two, okay, sum of these two, it also belongs to U plus W. So second property is satisfied. If I take any two vectors in U plus W, their sum also belongs to U plus W. Okay. So this is what is number 2, and number 3 says scalar multiplication. So I take any scalar C, I take any vector in U plus W like U plus W. Okay. Then can I write this as Cu plus Cw? You know, don't think that these are numbers. These may not be numbers. Initially, when I defined vector space, I said these are objects. So they could be any object. For example, they could be some polynomial, they could be matrices, they could be, they are not necessarily numbers. So this looks sometimes trivial or easy, that it is always be true, but these are not numbers. So one has to verify this. So this looks simple, but it need not be in all the cases. You have to verify it, because these are not necessarily numbers. These are in fact vectors or some objects, as I said. So how I can write this is because of the property of, you know, 8 or 9 property in that 10 axioms, where the scalar will distribute, its distributive property. This will distribute over this and this. So we can write like this. And how I can write? Because it's a vector space and it satisfies those properties. So we can write like this. So we can see that when we write like this, this part, it belongs to U. Why? Because U is a vector, is a subspace. This U belongs to U, and this is any scalar. So it is, if it is subspace, it must be closed under scalar multiplication, and hence this belongs to U. Similarly, this belongs to W. And so that means we have a sum, a pair where first part belongs to U, second part belongs to this, and that's why this must be in U plus V. So this suggests that this also belongs to U plus W. Okay. So here it should be small, this is small, these are vectors. So here suggests that any vector if I take in U plus W, scalar multiplication also belongs to U plus W, and hence it satisfies all the three criteria for U plus W to be subspace, and hence it is proved that if U and W are two subspaces, then their sum is also a subspace of V. Okay, so sum is also a subspace of V. Then let us consider simultaneously two examples, to see the sum can be of different types. That's how direct sum we can introduce. So we'll see what is direct sum. So to see, let us see two examples where we can see them separately. So again, let me take this V as R3, the Euclidean space, and two subspaces, let's say like this again. Now it is in R3, so there will be three components, and let's say this is 0, 0, C, and C belongs to R, any real number, and W is suppose A, B and 0, and where A, B, C all belong to the A, B, C, they all belong to R, set of real numbers. Now if you want to visualize this, this is nothing but this is nothing but those three axes we have to consider: x axis, y axis, z axis, and it divides the space into 8 quadrants, as you know. So what is this U in this picture? What is U? You can see it is x and y both are 0, only C will be there. C can be any number, so it includes all real numbers. So that means this is nothing but this z axis. Okay, this is z axis only. This thing is U. And what is W? It has x and y components, so it is nothing but this plane, xy plane. Oh. So this is x axis and this is xy plane. Okay. So if you see this, let me draw like this. Okay. Of course it will extend like this, it will extend like this, so this will extend like this. So this is that z axis. Okay. So the plane is this blue part, and this set U is only this line, this axis. So if you can imagine what is the intersection, what is the common between these two, only it intersects at the origin. So this is the only intersection between the two, U intersection W, which is 0 vector. Okay, their intersection is only this. Okay. So if we take the sum of these two, if we take, so U plus W, if we take the sum, it will be elements of the form A, B, C, where A, B, C, they belong to R. Okay. So this is nothing but what? This is our V, okay, which is R cube, R3, the whole space. And as you know, this is the sum is a subspace. So, in this case this u plus v where it becomes R3, which is the space, and that is a vector space. So, this is obvious, but let us consider another example to distinguish between these two cases. What is sum of two vector spaces and what is direct sum. So, another example, let us consider same v is equal to r cube, but this time u, I am using same notation, but then they are different. So, here let us say a b 0, okay, I am writing in short, a b belongs to r, and w is suppose 0, c and d, suppose like this. It contains vectors of this form. Now, you can see what are these two in, if you want to visualize in the figure, in picture, then this is nothing but their x and y components. So, it is x y. If we again consider this, the space, three-dimensional space is x, y and z. So, in this what is u? U is x and y are there. So, it is this xy plane, the xy plane, and then this is yz plane, y and z, which is this part, only positive quadrant if we consider. So, what is the difference between these two? Here the two sets, they intersected at only one point 0, but here what is the intersection of these two? One is this xy plane, another is this yz plane. So, you can see the common is this part, okay. That means this y axis, okay. So, what is common between these two? It is set of the form 0 b 0. That means the whole x axis is the common part, whole y axis is common part of this u intersection v. So, this is the intersection here. So, the difference between the two is here the intersection is only at one point, that is the 0 vector, and here the whole y axis is the common part between these two. Okay. So, here also what is the sum? Sum will be like u plus w. In this particular case, it will be again a, b plus c and d, okay, like this. So, again this is nothing but the whole space, this again is R3, okay. So, the difference between these two is through an example also one can see. Suppose I take any element from V, I take any element, let us say 1, 2, 3. So, 1, 2, 3 it belongs to R3 or the space V here, I am talking about this. So, this 1, 2, 3 one can write, I can write is like 1, 0, 0 plus 0, 2, 3. So, this belongs to U because it is of this form. First component non-zero, second, third component can be anything, B can be anything, it can be 0 also. So, this belongs to U and this belongs to this. So, you see I can even write that this B0 can be anything, AB0. So, I can write let us say 2 here I can write. No, I can write 1 here. Instead of writing 0, I can write 2 here. I can write this and I can get the same 1, 2, 3 vector. I will write 0 here, 0 here, I can write 3 here. So, you can see this writing as sum of two vectors is not unique in this particular case, whereas here it will be unique. If you add any vector here, any vector if I take in this space again here, then as sum of these two sets we have to write uniquely. For example, the same thing if I want to write here in this example, so I have to take any element here. So this element I have to write this as 3 only, plus, and if I want to write an element from here, I have to write 1 to 0. There is no any other option. Okay. So writing of any vector in this particular example where they intersect only at one point is unique. This sum is unique. Only in this way one can get this vector. But here in this particular case, when the intersection is not a point, it is the whole line is common. So in this case we have infinite ways of writing a sum of two vectors. So depending on this we define what is the direct sum. So now we are defining direct sum, this concept. Okay. So this is the definition. Okay. Definition. So U and W. Suppose there are two subspaces of V. Then we say U plus W, which is sum of two spaces that I defined already. So this we say this is a direct sum okay if U plus W can be expressed as U plus W uniquely. Okay. So this uniqueness is introduced in direct sum. Okay. So there is a theorem on this. Let V be a vector space and U and W be two subspaces. Okay. Then U plus W is the direct sum if and only if U intersection W is 0. So the intersection, as I have given one example, the first one where the intersection was the singleton set, it contains only 0. So this theorem, it is if and only if. If it is direct sum, then this intersection has to be 0. If it is 0, then the sum must be direct sum. So there is a simple proof where I'll end with this one. So there are two parts. It is if and only if. I mean, both way you have to prove. So first way, like this, if we want to prove, that means I'll assume that U plus W be the direct sum. Direct sum means what? Then when we the elements here can be expressed as sum of elements here and here uniquely. So then what we need to prove? That U intersection W is 0. So to prove this, I'll assume any element. Let V belongs to U plus W. I'm taking any element here. So what I have to prove? V must be 0, because this contains only 0. So we know that V, I can write 0 plus V or V plus 0. Okay. How I am writing? Because this is an element here. So the elements here, they will have two components. The first one from U, second one from V. So this says this belongs to U and this belongs to W. Similarly here, this belongs to U and this belongs to W. Okay. And we have expressed V in these two forms. But then what this assumption says, we assume that this is a direct sum, means by the definition this will be direct sum when the expression like this will be unique way. That means these two must be same way of writing. When this will be, so this, if these two are same, then these two components must be same or not. Similarly, this V must be 0 if it is unique way. So from our assumption, we know that this 0 must be same as V, because this is a unique way of writing as sum of two vectors from U and W. So this V must be 0. Then only it will be unique way. If it is different, then it will not be unique way. Okay. So this we wanted to prove, V belongs to this and V must be 0. So V is any element here, and if any element is always 0, then this contains only 0. Sorry, this is not this one. We wanted to show this 0, so it is intersection. Okay, so V belongs to intersection, means V belongs to here and V belongs to here. So this V belongs to W as well as V belongs to U, we are writing here. And hence, when V is 0, any element in intersection is 0, that means, so what we have proved is intersection of this is 0 only. Okay. Then finally, we have to prove this way, that means the converse part. So here we'll assume, what we'll assume? The other way, assume that W intersection, U intersection W is 0. This will assume it contains only these two vectors. So now we have to show what we have to prove. We are assuming this, but to prove what? To prove that the elements here can be expressed as sum of elements uniquely. So suppose, if possible, the contrary we are assuming, the contrary. Suppose there are two ways of writing the elements in here. Okay, two ways. So V, suppose we can write U1 plus W1. Okay, this V can be written in two ways. So U2 plus W2. We are writing the same element in U1 plus, this time this belongs to, V belongs to U plus W. Okay, this is an element here. So if it is an element here, we know it can be written as sum, this type of sums, and we have to prove that this type of sum, when I write a vector, this must be unique. Only one way of writing this. But to prove this, we are assuming the contrary. Suppose there are two ways of writing this sum, the same vector, so they are equal. So from here, can I write U1 minus U2? It seems like taking U2 here, but it's not that obvious. And similarly, W2 minus W1. So what are the meaning of U1 minus U2? U2 minus U2 is by closure property of scalar multiplication, it is minus 1 into u2. So that belongs to the vector space, and hence it is sum of those two vectors u1 plus minus u2. So anyway, so we can write like this, no problem. But then if these two are same, okay, and this element belongs to where? This element belongs to, because both u1 u2 belong to u, this set, the first set. So their combination u1 plus minus u2, it is closure property of addition, is belongs to u. Similarly, this belongs to w. Okay. So these two are same and they belong to u as well as this. Okay. That means both this belongs to u intersection w, u intersection w. This also belongs here. This also belongs here. Why? This belongs to u, this belongs to w, but they are same. Okay. So both this belongs to the intersection. Now if this belongs to intersection, this also belongs to intersection, and our assumption is that intersection is only 0. It contains only 0. That means these two elements must be 0. So both must be 0. So if it is 0, then what we have proved is u1 equal to u2 and w1 equal to w2. So from here you can see what we have proved, the uniqueness of the expression of the vectors in u plus w. If I write two vectors in two different ways, then it is all the same, one and the same, because u1 is same as u2, w1 is same as w2. So that means if what we have proved, if the intersection is 0, then we can express the vectors as sum of two vectors in u plus w in a unique way. That means, you know, if this can be done, then what we have proved is that u plus w is the direct sum. And in the definition we should have mentioned the direct sum. There is a specific notation. It is denoted with plus and the circle here and w. So this is the direct sum of u and w, and when we write like this, this is the ordinary sum. Both are subspaces, but this is called direct sum, and it has a lot of applications that we cannot discuss here today in this short video. So thank you all for your attention. Thank you.